Physics Chapter 4 Mass, Weight, Inertia and Density. Lesson 3 Weight. Now in this video, I will try to help you understand a little bit more about this concept called weight. Okay, weight is defined as a pull or force of gravity acting on a body. Now instead of writing down weight, for us physicists, we sometimes like to shorten it, so therefore we use a symbol capital W to represent weight. Okay. Take note as well that weight is a vector quantity and therefore it means that it has both magnitude and direction. Okay. And lastly, the SI unit for weight is none other than the Newton and with the symbol capital N. So do take note that when we are writing down the symbols for weight and the unit Newton, take note that both of them has to be in capital letters. Now, always take note of this. It is always important to remember that the weight of an object depends very much on gravity. In other words, the stronger the gravity is, the higher the weight. Or the weaker the gravity is, weight will become less. Right, how do we measure weight of an object? Okay, we use two instruments. The first is known as the spring balance. These are examples of the spring balance. In fact, in our real life, we do actually notice that those newspaper collectors, known as Karang-Guni in Singapore, they actually do use this to measure the weight of the newspaper they collect. Okay, and the other one is known as the compression balance. I'm sure you have seen one of these before. Okay, during at the Pasar Malams. So let's try to understand a little bit more about this concept weight. Okay, let's recall that weight is actually the pull or force of gravity acting on a body. Okay, so what does that mean? Right, so let's have a look at this Earth itself. Okay, now around the Earth itself, there's this invisible region whereby if we were to place an object with some mass inside this region, be it at the top here or right at the bottom or to the right or even the left, this object itself will experience a force that is directed towards the Earth. Okay, now what happens if we were to have an object outside of this region indicated by the white arrows? Well, if I have an object that is outside this region, this object itself, even though it has mass, will not experience any force towards Earth. Okay, so in other words, it's very much like a magnet. If I played with a magnet before, you'll realize that, hey, if I had to have a circular magnet and another piece of, let's say, a paper clip positioned at this location, well, take note that this paper clip is outside the effect of the magnetic field around this circular magnet. Well, that paper clip will just remain there, isn't it? It won't just be attracted towards the magnet. However, if I had to move that paper clip into this region, all right, and well, you know exactly what's going to happen next. This paper clip, it will actually be pulled towards a magnet. Okay, so, well, in that sense, the Earth's gravitational field is similar to that of a magnetic field effect. So the next question is this: do all gravitational fields have the same effect on an object with the same mass? Okay, let's say if I have an object that is 10 kilogram, if I had to move it from Earth to the Moon and then to the Mars itself, planet Mars itself, would this 10 kilogram object experience the same pull of gravity? Well, the answer to that is obviously no. Okay, so we will have to actually define the gravitational field strength for different places, for different planets. Okay, so let's have a look at how do we define gravitational field strength. Gravitational field strength is simply defined as the amount of gravitational force or pull acting on a body with a mass of 1 kilogram. And instead of writing down the full 3 words gravitational field strength, which is very long, well, we scientists would like to just use a simple symbol, small g, to represent that. Okay, the SI unit of gravitational field strength is none other than the Newton per kilogram. Okay, or sometimes you will see it expressed in meters per second square. And well, we have come to this point whereby let's find out what's Earth's gravitational field strength. And Earth's gravitational field strength is 10 Newton per kilogram. So we have come to a point whereby we now know that the weight of an object depends on a few things. Well, first, it depends on the mass of the object, and secondly, it depends on the gravitational field strength of that particular location. So how do we then calculate weight? Well, the weight of an object can be calculated with this simple formula. Weight is equals to the mass of the object multiplied the gravitational field strength where the object is. In short, in symbols, we like to represent it this way. Weight has the capital W, and we equate that to small m multiply small g. SI unit for weight, let's recall, is the Newton, expressed as a capital N. Okay, and to work this formula itself, take note, we will have to use the kilogram as a unit for mass, and also the Newton per kilogram as a unit for GFS. So now let's have a look at how we can make use of the formula to calculate weight. If you have this particular problem, whereby the astronaut has a weight of 67 kg and you're asked to find his weight on the Earth and Moon, given that the gravitational field strength on Earth is 10 Newton per kilogram and the gravitational field strength on the Moon is 1.6 Newton per kilogram. Well, it's just a simple maths application. So how do we solve? So let's have a look at the presentation of the calculation. So weight of the astronaut on Earth is simply equate to m times g, mass times gravitational field strength. And the next step is just write it down, 67 kg multiply 10 Newton per kilogram for the GFS or gravitational field strength on Earth. And we get a 670 newtons. That's how much the astronaut would weigh on Earth. Now let's have a look at what his weight is on the Moon. So writing down the equation again, m times g, or gravitational field strength on the Moon, we still have the same mass, right? So recall that the mass of an object remains the same, unchanged regardless of location. And then we multiply that with 1.6, the gravitational field strength on the Moon. And that will give us 107.2 newtons. So let's compare these two values. Obviously, it's about 6 times lesser on the Moon. Well, another fact to take note of is this. Weight of an object depends as well on the distance. So what do we mean by that? Well, it simply means that the pull of gravity decreases when distance from Earth, for example, increases. This simply means that the further away we are from the Earth's surface, we'll find that the pull or the force of gravity will become less. Okay, this is because the gravitational field strength becomes lesser and lesser the further we are away from the planet's surface. So the question would be this: would you weigh the same on Mount Everest and on the ground? Well, now you know the answer. On Mount Everest, you will actually weigh less than on the ground itself. So that brings us to a very interesting thought, isn't it? So if let's say your weight on the ground is, let's say 800 newtons, and if you were to take a trip on an aeroplane to for holidays, for example, well, if the plane is flying way high up in the sky, what do you think will happen to your weight? Will it be the same, 800 newton, more or less? Well, if you had not eaten anything on the flight itself, well, your weight would actually be less, isn't it? And there you go. By just taking a plane ride, you have lost weight. But the point here is, have you actually lost any mass? Think about that. Now, let's have a look at this checkpoint 2. A satellite is launched from Earth into orbit. What do you think has happened to the mass and weight of the satellite? Which of these 4 choices would be the right answer? Well, the answer is obviously C. Recall that mass will always remain the same, regardless of location. However, since we are moving the satellite from Earth into orbit, the further it goes away from Earth, the pull of the Earth's gravity will become less, okay? And that is because the gravitational field strength on Earth will become less as we move further away from the planet's surface. So the weight will decrease as well. Checkpoint 3. Which statement correctly describes the mass of an object? This is simply a recall question. So let's recall that mass of an object is the amount of substance the object contains. So the response is B here. So at this point, I think it will be good for all of us to understand the differences between mass and weight. Okay, first and foremost, always remember this: mass is not the same as weight. Mass is the amount of matter in a body, while weight is actually the pull or force of gravity acting on the body. Mass is a scalar quantity. It has only magnitude but no direction. But weight is a vector quantity with both magnitude and direction. Mass is measured in kilogram, while weight is in newtons, capital N. Mass of an object remains constant regardless of place or location. However, weight of an object changes from place to place depending on the gravitational field strength of that location. Mass can be measured by a beam balance or electronic balance, while weight can only be measured by a spring balance or a compression balance. With that, thank you for listening.